Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of this lecture is Capillary Viscometers, Errors and Corrections, Part 2. We have been discussing how to measure rheology of a unknown fluid using a capillary viscometer. That is what we have been discussing in last two classes, right. So, then we have a recapitulation of what we have studied in last two classes. Capillary viscometer for rheology of generalized Newtonian fluids or time independent non-Newtonian fluids. When you apply capillary viscometer or when you use capillary viscometer for rheological measurements of time independent non-Newtonian fluids. So, then how to design or how to develop the working principles in the sense the equations that are required to obtain the shear stress, shear rate, etc. we have already discussed. So, what we have we find that shear stress using capillary viscometer, that you can get it as a tau w is equals to minus delta p by L r by 2, right. So, the wall shear stress. So, that means if you know the pressure drop, so then you can obtain the wall shear stress without any difficulty, and then in obtaining this relation we have seen that the fluid nature or nature of the flow, whether laminar or turbulent or transition region, which region of the flow that we have not considered, and then nature of the fluid also not brought into the picture until we finding this relation tau w is equals to minus delta p by L r by 2. That means as long as the flow is fully developed, incompressible and steady, then we can use this relation for any fluid that is flowing through a capillary, right. So, then specific to the fluid, then shear rate expression we have obtained. The shear rate, wall shear rate expression for time independent non-Newtonian fluids or generalized Newtonian fluids, we found it as gamma dot w is equals to 3 n prime plus 1 by 4 n prime 8 v by d. This 8 v by d is a nominal shear rate or apparent shear rate for non-Newtonian fluids, and it is true shear rate for the case of Newtonian fluids. So, if you wanted to have the true shear rate for non-Newtonian fluids, especially time independent non-Newtonian fluids, then you have to have a correction factor. That correction factor is nothing but 3 n prime plus 1 by 4 n prime, right. Then n prime here we found it as nothing but d log of tau w divided by d log of 8 v by d, that is shear stress versus apparent shear rate when you plot on a log scale, whatever the curve that you get. So, that slope different tau w that you can find out, that is nothing but n prime. Okay. Then after that what we have seen, after though we have a relations to get the true shear stress and true shear rate information for a time independent non-Newtonian fluids, then what we realize that there are several possible sources of errors existing in these measurements. Because what we have seen, what are the primary assumption that we have taken? We have taken that flow is laminar, fully developed, steady, and then fluid is incompressible. So, then obviously when the flow is not fully developed, so then there would be some errors, and then if the flow is not laminar region, if the flow is not within the laminar region, then again there will be errors like that. Different errors are possible. So, we have enlisted all such kind of errors, and then we have seen primarily end effects, wall slip effects, and deviation from laminar behavior, then kinetic energy losses due to the sudden contraction of cross section area at the connection or at the point where we are connecting the capillary to the barrel, right. Then variable fluid head, then viscous dissipation, and so on. So, we have seen several errors are possible, right. So, what we have seen, some of them may be minimized, or we can get rid of some of these errors by making small changes in the design, or just operating in such a way that some of these errors are negligible or even or completely disappear. That is possible, but what we have seen, this end effects and then wall slip effects are very essential. So, then accordingly what we have started, we started with the end effects in the previous lecture. What we have seen, because of the end effects, they cause increased pressure drop at the entry, at the entry because of the sudden contraction of the flow area. So, there is a increased pressure drop. So, then we have to find out how much that increased pressure drop, so that we can make adjustment in the rheological measurements, and then that we had a method, and then we found how much pressure has increased at the entry, that we found, and then that pressure we subtracted from the overall experimentally measured pressure. So, whatever the corrected pressure is there, that we have used to obtain the corrected wall shear stress, right. Because of the entrance effects, what happens, the pressure is increasing. If the pressure is changing, the change in pressure is occurring. So, then obviously that will show influence on the shear stress, because shear stress is directly proportional to pressure gradient. That is what we have seen. So, then accordingly, once we found out how much is that pressure increase, that pressure we have subtracted from the measurable or measured pressure drop, then we have obtained the corrected wall shear stress, corrected for the end effects. So, that is what we have seen, and then after seeing that procedure, we have also seen an example problem, because of which what we realized that after incorporating the end effects, the rheological behavior by using different lengths of capillaries, they are all superimposing onto each other. Before incorporating the correction for the end effects, they were not superimposing onto each other. That is, shear stress versus nominal shear rate, they were giving different curves for different L values, different L values of the capillary. But after incorporating the end effects in the shear stress calculations, then that corrected shear stress versus nominal shear rate or apparent shear rate, when we plotted, we found that all the curves, all the data from different capillary lengths are superimposing, that ensuring that the correction for the end effect has been incorporated, right. So, now in this lecture what we will be seeing is the wall slip effect. First we discuss what it is, and then we see how to make amendments, corrections because of that because of such existing wall slip at the wall, okay, at the capillary tube wall. That is what we are going to see now. So, wall slip effects are very much essential, especially in the case of multiphase non-Newtonian concentrated suspensions, foams, emulsions, polymers, etc. Right. It has been found that in the case of confined narrow passages, the role of wall slip becomes more important, right, confined narrow passage. So, that means diameter is playing a role, right. Let us say capillary, you are in the context of capillary, if we talk, if the confinement increasing or decreasing, that means diameter increasing or decreasing accordingly, right. So, when we it has been found that if you change the diameter, that is, so the wall slip whatever is there, that is playing essential role, very important roles of it plays essential role on the rheological behavior or overall flow equations or flow data that we are getting. Okay. So, it has been found that substantial importance of wall slip effect in the case of confined narrow passage. That means, the passage whatever is there, if that decreases, the wall slip effects become more and more significant. We started taking the narrow passages because we wanted to have the variation in the shear stress or variation in the shear rate from center to the wall of the capillary should be negligible. With that purpose, we have started the equation development, etc., by taking narrow passages, narrow capillary cylinders, like that we have taken. But when you take such kind of narrow passages, then wall slip will become significant, and then accordingly correction should be provided. So, how does it occurs? The so called apparent slippage, how does it occur? That we have to understand. Actually, there are different types of slips have been reported. So, one is the true slip, another one is the apparent slip, which are relevant as of now. True slip in general occurs in the case of low viscosity fluids or gases, where the attraction between the molecules of the low viscosity fluid or gases and this wall, whatever the container wall or capillary wall, whatever you have taken. So, there is a attraction force obviously. So, at higher shear stress, at higher shear stress, what happens, these molecules overcome the attraction force whatever is there between the molecules of these gases and then this solid surface. That attraction forces would be overcome by these gas molecules or low viscosity fluid molecules, especially at higher shear stress, and then because of that one there will be a depletion of fluid layer at the surface of the wall, and then because of that depletion the local viscosity at the wall would be much more lower compared to the bulk viscosity of the fluid in the bulk region. Because of that depleted viscosity or depleted layer at the wall, so the velocity of the fluid rather becoming 0 at the wall, it will be having some substantial velocity, and then that velocity is the slip velocity. And then such kind of slip velocity in the case of low viscosity gases, because of the overcoming the attraction force between the molecules and then solid wall surface at high shear stress, that is called as a true slip in general. But such kind of slippage would also occur in the case of high viscosity fluids like non-Newtonian fluids, concentrated suspensions, etc. as well. What happens in the case of high viscosity non-Newtonian multiphase concentrated suspensions, when they are flowing through narrow passages, that is important, when they are flowing through narrow passages, layer of fluid near the wall is depleted, and this layer is very thin and dilute compared to the bulk fluid, its viscosity is low, and then this layer has much lower viscosity compared to the bulk viscosity, resulting in apparent slippage of fluid at the fluid along the wall, right. So, now this causes because of this depleted layer at the wall, the local viscosity becomes very less, so then obviously the velocity would be high, because the resistance amongst the fluid molecules is less if the viscosity is less. So, then viscosity is decreased, that means the velocity at the wall would increase. So, because of that one, at the wall rather having the no slip velocity or 0 velocity, we will be having a apparent slip velocity that would be having substantial value if the passage area is very narrow, if the fluid passage area is narrow. And then it has been proved that it is of great value in explaining anomalous results for the flow of non-Newtonian fluids in small diameter tubes. We are going to see with an example as well. We do certain kind of simplifications or design equations whatever we have developed previously for the case of shear rate, nominal shear rate. Those equations would be corrected, and then new equations when we use. So, then again we can see that after incorporating the wall slippage, the shear stress versus apparent shear rate information by using different capillaries does not show different curves, all the curves would be superimposing onto each other. Okay. And then this apparent slip is often encountered in the case of non-Newtonian fluids like in food processing applications, narrow flow geometries such as concentric cylindrical rheometers, parallel plate rheometers, cone end plate rheometers, narrow opening capillary viscometers, etc. So, that means in almost all rheology measuring systems or rheometers or viscometers, what we have we may have a fluid slippage at the wall, because in all such kind of geometries in general we have narrow passages. Why narrow passages we select? In order to reduce the difference in the shear stress from the wall to the center, or to reduce the difference in the shear rate from the wall to the center. So, that reason we have taken the narrow flow passages for these kind of rheometers, but that is inducing apparent slip. And another application where we can find apparent slip in the case of non-Newtonian fluids is extrusion of pasty materials, polymeric solutions, etc. Then flow of macromolecular polymeric mels and solutions in narrow gaps, and so on. Further, in the case of structured materials as well, slip phenomena may occur. Some example is in porous media. If you have a porous media, even if the fluid is a Newtonian fluid, it is a low viscous liquid, then also slippage or slip phenomena would occur. So, that is quite possible. So, slip phenomena may possible even in the case of structured material like in the example of porous media, then microfluidic devices, and then extrusion dies used in food and polymer processing applications, etc. So, how do we realize? So, now what we do, how do we realize this slip is existing or not, that pictorially we can discuss now. So, what we have a tube wall, let us say capillary only we can take, no problem. We have a tube wall and then let us say coordinate systems you are taking like this. So, this is y direction, this is z direction. So, fluid is moving in the z direction, the velocity whatever is there, that is function of y, Vz is function of y. Okay. So, then at certain z value which is in the fully developed region. So, if you draw the velocity profile, you can have a curve like this, that is at the wall there is no velocity. So, 0 velocity, and then gradually if you moving up, so the velocity of the fluid gradually increases and then it reaches maximum value at the center of the capillary. That is what we have seen in the case of no slip. When we take a no slip assumption when the fluid is flowing through capillary, so this is what we have. Right. Now, if you wanted to know the shear rate at the wall, so what you do at the wall, at whatever the z location you consider, because it is a fully developed flow. So, then whether you consider any z value, it would be fine, right. So, you draw a tangent to the velocity curve and the velocity profile at the wall. What you do? You draw a tangent like this and then find out the slope of that curve, that is nothing but dVz by dy at the wall, that we call wall shear rate gamma dot. Okay. This is what you in general have in the case of a no slip boundary condition that we use when the fluid is flowing through capillary or confined region, something like that. Okay. So, now, but if there is a slip, what happens? The same situation now we have the tube wall and then fluid is moving in the z direction and then velocity is changing in the y direction like this. So, this is z direction, this is y direction. So, Vz is function of y here again, right. So, now velocity profile if you draw at any location, let us say at this z location, if you wanted to draw the velocity profile, here again it is fully developed flow. What happens at the wall? Now, we do not have a V is equals to 0. Here in the case of no slip condition, what we have seen, Vz is equals to 0 at y is equals to 0. But now here, because of the depletion of fluid layer at the wall, especially in the case of non-Newtonian concentrated suspensions. So, depletion of fluid layer at the wall will take place. Because of that one, the velocity of the fluid layer at the wall would be certainly having certain larger value, it will not be 0. So, that value is now we are calling is Vs. And then after that, as you move further away, what happens? Again gradually the velocity increases, same like in the previous case. But now the magnitude, overall magnitude of the velocity, if you see a different y values compared to the previous case. So, what you can see, the velocity is higher at every location. Because of this one, what will happen, you will be getting higher flow rate than expected. Whatever the flow rate you expect when you take no slip boundary condition, as in the previously we have done analysis. So, whatever the flow rate that you are expecting, you do the you have all the equations, etc. So, then without doing experiments also you can get a certain kind of value. So, that should not be an issue, right. So, whatever the pressure drop, for a given pressure drop, whatever the velocity you expected, compared to that you get higher velocity or higher flow rate you will get if there is a velocity slip at the wall. Okay. And then if you wanted to know the shear rate at the wall, now at this point you have to draw the tangent again in the similar way, right. So, then the tangent slope of the tangent whatever you are drawing at the wall to that velocity profile, what happens, that will be having the slope smaller than the slope in the case of no slip condition when you are applied. So, that is dVz by dy at the wall. In the case of wall slippage, you will be having gamma dot s, which is smaller than the gamma dot, and then this gamma dot for no slip condition, and then gamma dot s is for the wall slip condition. Okay. So, depleted layer of fluid at wall has higher velocity than expected no slip velocity for narrow passages, thus leading to higher flow rates than expected at a given shear stress, or otherwise lower shear stress resulted than expected for a given value of the shear rate. Okay. So, this leads to errors in interpreting experimental results if appropriate allowances is not made. How much error that is going to be, you cannot qualitatively say something and then say that that error is negligible, because by seeing one example problem you will be realizing that velocity is substantially higher. It is substantially higher, that we can see by one example problem. The data is also a true experimental data. Okay. So, wall slip in the context of capillary viscometers. Wall slip may give rise to inconsistent wall shear rate, because now what we have seen, because of the wall slippage at the fluid slippage at the wall of the capillary, the flow rate is higher. So, if the flow rate is higher, then obviously the velocity would be higher, average velocity would also be higher, because the cross section area is remaining same. So, that higher velocity is giving inconsistent or not reliable shear rate at the wall of the capillary, because velocity is related to the shear rate now, right. So, pressure drop is related to the shear stress that we have seen, volumetric flow rate or average velocity is related to the shear rate. So, now there is a inconsistency or inaccuracy in the measurement of velocity or flow rate. So, that inconsistency or inaccuracy whatever is there, that will be reflecting in the value of wall shear rate. Okay. So, we have to make corrections. So, this error may be there even when you incorporate corrections for all other rest of the errors, whatever so many possible errors we have seen, you incorporate or make amendments accordingly, so that all other errors have been taken care. Despite of that one, if there is a wall slippage, so that is going to give inconsistent or inaccurate results or rheological behavior of a unknown fluid. Okay. Thus, it is essential to quantify effect of wall slip on shear rate, and then that is what we are going to see now. And then because of wall slip at the tube wall, now Vz is equals to Vs. At tube wall, in the case of no slip velocity, we have taken Vz is equals to 0, but there is a fluid slippage at the wall. So, now we cannot say Vz is 0 at r is equals to r, but it is having certain value Vs. What is this Vs? We do not know. As of now, we do not know what is this Vs, but we will find. There is a method, a reliable method that we can go through and then make corrections for this Vs as well. So, volumetric flow rate for the case of a fluid flowing through a capillary, we have seen it as dq is equals to 2 pi r Vz dr. Vz is function of r. And then when you do the integration here, 2 pi is a constant, integration of r is r square by 2, Vz is as it is, then minus, then integration of r is r square by 2, and then differentiation of Vz is dVz by dr. So, then what I am doing, I am writing minus dVz by dr, and then here I am writing plus and then dr. So, this is what we have seen. Now, if you substitute the limits here, r square, capital R square by 2 Vz at r is equals to r minus 0 square by 2 Vz at r is equals to 0. So, since this term is anyway 0, because 0 square is there. Now, in the previous case, when we were designing equations to measure the shear rate of a fluid using a capillary viscometer, previously what we have taken Vz is 0 at r is equals to r because of this no slip boundary condition. But now we realize that when you use such equations we are getting anomalous results. So, then we realize that there may be certain thing like called wall slippage. So, that slippage because of the wall slippage, the fluid velocity whatever is there at the wall at r is equals to capital R, that is now Vs. It is not 0, but it is Vs. So, then what we have 2 pi r square Vs by 2, that is pi r square Vs, plus this term is same as our previous derivation that we have done when we are designing the equations for the capillary viscometer. Designing the equations, that means deriving the equations for shear stress and shear rate when we are using capillary viscometer. So, this term is going to be same, and then we have to follow the same thing, but we are not going to do any integrations etc., all that are not required now. So, after substituting these limits, and then simplifying, then this is what we have for q. Q is equals to pi r square Vs plus pi integral r square minus dVz by dr, right. So, now this volumetric flow rate is having two contributions, one contribution because of the fluid slippage, another contribution because of the fluid no slip condition Q and S, right, and both of them are addendum. So, RHS of above equation has two contributions to total volumetric flow rate resulting from no slip velocity condition and then slip velocity condition. Because of the slip velocity condition Qs, let us call it Qs first term in the RHS, and then because of the no slip whatever the volumetric flow rate is, that is the Qns, that is the second term. Okay. So, where Qns is same as derived in the section of working principles of capillary viscometers, and to recollect, this is what we got it previously, right. And then we found that this right hand side integral part whatever is there, you do the differentiation both sides with respect to tau w, and then we get into the Leibniz form, and then we have done all subsequent steps we have done, and then we found that this is a constant. After doing the integration and substituting the limits, you will get a constant, or in terms of tau w you will get, and tau w is a constant for a given pressure drop. Okay. So, but anyway we do not need to do anything now. So, now the equation number 1, that is whatever the q is equals to pi r square Vs plus pi integral r square minus dVz by dr is there. This equation we are dividing both sides by pi r cube tau w. So, that q by pi r cube tau w in the left hand side, right hand side you will be having Vs by r tau w plus whatever the integral part that is there, we are not worrying, we are not doing it, just giving a notation Qns to the Qns, we are giving notation Qns to the second term in the RHS of equation 1. So, Qns divided by pi r cube tau w. Okay. So, first term in the RHS is nothing but pi r square Vs, if you divide it by pi r cube tau w, then you will be having Vs by r tau w, right. Now, q by pi r cube is nothing but 2V by d. So, in place of q by pi r cube we will be writing 2V by d, and then both sides we will be multiplying by 4. The first term in the RHS whatever is there. So, what we have Vs by r tau w. So, then in terms of d we can have 2 Vs by d tau w. So, we multiply and then multiply by 4 both sides. So, then you will be having the first term in the right hand side as 8 Vs by d tau w. So, left hand side 8 V by d multiplied by 1 by tau w is equals to 8 Vs by d 1 by tau w is the first term in the RHS, and then this term in terms of d if you write 32 Qns by pi d cube tau w, and then Qns we find it is a constant. In terms of equations also it is coming in terms of tau w, that is what we have seen. So, then altogether what we understand, this equation equation number 3, second term in the RHS is constant, first term in the RHS it is having two values Vs and D, two parameters Vs and D are there, both are changing. If you are changing D, so then Vs is also changing if there existing a wall slippage. So, we are taking the cases where there are wall slippages are there. Remember, if you have a large diameter capillary, so then wall slippages may be very small, you may avoid it. But when you take the large diameter capillaries, then shear stress and shear rate both will change from center to wall. So, then you cannot assign one single value of shear stress or shear rate. Okay. So, in the left hand side, what we have the average velocity V and then D. So, what we do from this equation, if you plot 8 V by D versus 1 by D, then what will happen? It is possible that you can get a straight line of slope 8 Vs, right. So, that is what second term in RHS is constant for a fixed value of tau w, and then for a range of tau w values you get data 8 V by D versus 1 by D from the experimental results, and then you plot it 8 V by D versus 1 by D, then you will get a straight line with slope Vs, right. So, you may be thinking why tau w, because it may be cancelled out. No, because what we wanted to get a relation for different shear stress, because now what after incorporating all other corrections, shear stress is true shear stress, that is reliable, because all other we assume that all other errors whatever are there, corresponding corrections have been incorporated such as end effects etc. So, whatever the shear stress that we get, that is a reliable, right. So, that is the reason for different values of shear stress we are trying to do this information, so that we get some value for the velocity slip. Okay. So, now final wall slip corrected apparent shear rate would be nothing but 8 V minus Vs by D. Actually 8 V by D is nothing but apparent or nominal wall shear rate, is not it? Now, after realizing there is a fluid slippage at the wall, that is fluid is having certain velocity at the wall. So, then that velocity we have to find from and then subtract from the average velocity and then multiply by 8 and divide by D to get the wall slip corrected apparent shear rate. Remember, this is also apparent shear rate only. It is not the true shear rate if it is a time independent non-Newtonian fluid, right. It is still a apparent only, but apparent shear rate also having some errors, some anomalous because of the change in diameter. If you change the diameter of the capillary, different shear rate values you are getting because of the wall slippages. So, then how much wall slippage is there, or what is the velocity at the wall because of the wall slip effects, that you find out, and then you are subtracting that one from the average velocity V, and then getting this corrected wall slip corrected apparent shear rate. Okay. So, then true shear rate, if you wanted to get that, again 3 n prime plus 1 by 4 n prime calculation you have to do and then multiply it. Okay. True shear rate after making wall slip corrections, we will be having 8 V minus Vs by D multiplied by 3 n prime plus 1 by 4 n prime. That n prime is nothing but d log of tau w divided by d log of 8 V minus Vs by d now. Not d log of 8 V by d like previous case, d log of 8 V minus Vs by d, because now 8 V minus Vs by d is now the reliable apparent shear rate or wall slip corrected apparent shear rate. Okay. We will take an example problem also now to understand about this one. So, example problem to realize how much important to establish wall slippage effect in the case of capillary viscometer, and then how to make the correction for the shear rate in apparent shear rate by using that slip velocity at the wall and then finding out the true rheological parameter of the fluid. That is what we are going to see through this example problem. Okay. For a 0.5% partially hydrolyzed polyacrylamide in water solution, the following data is available for 4 capillaries of the same length. Length is same 374 mm, but of different diameters. Obtain the true shear stress, true shear rate for this polymer solution. Okay. Tau W gamma dot we have to find out. End effects may be assumed to be negligible because the minimum value of L by D is 340. For time independent fluids, L by D more than 150 itself is sufficient to avoid or to say the end effects are negligible. But now in the case minimum value of L by D is 340. Why minimum? Because there are 4 different values of D. L is constant, right. So, now when D is 0.191 mm, Q versus delta P information is given here, first 2 columns. Third and fourth column for D is equals to 0.266 mm, and then fifth and sixth column for D is equals to 0.626 mm, and then last 2 column when D is equals to 1.1 mm, the Q versus minus delta P information is given. Pressure drop is given in kilopascals, volumetric flow rate is given in meter cube per second. So, then Q multiplied by 10 power something is there 9, 10, 11. So, then whatever the values are there, they should be multiplied by 10 power minus of this whatever the 9, 10, 11 etc. Okay. So, now first what we have to see, wall slip effect is required or not, that is what we have seen. We have to see, because what we have seen in the previous class, we have established how to make correction for the end effects. But now it is saying that in the problem statement itself says that neglect the end effects because L by D is 340, minimum L by D is 340, right. 374 divided by 1.1 if you do, so then you get approximately 340. Right, 374 by 0.191 mm if you do it, you may be getting much higher value of L by D. So, that is more than sufficient to say that the end effects are negligible. So, now the only other effect that we are discussing is wall slip effect, right. So, in order to know whether the wall slip effect is required or not, this information first we have to convert in terms of tau W versus 8 V by D apparent shear rate. Wall shear stress and then apparent wall shear rate we have to get by using this data. Very simple, because tau W you can get minus delta P by L, D by 4 you can do, and then Q is given. So, then V average you can get, V average equals to Q by pi r square, that you can get. So, then this nominal shear rate also you can get for each data set, right. Then you plot them on a graph tau W versus 8 V by D. If they are superimposing onto each other for all 4 cases of capillary diameters, then we say that no other correction is required in the case of whatever this apparent shear rate is there, and then we can directly find out its rheological parameters by finding out the n prime etc., those kind of things. Fine. So, that is what first we are going to see. If they are not superimposing, that means wall slip is playing role, because diameter when you are changing, that means the passage cross section of the passage you are changing, right. So, if you have the cross section narrow cross section passage, then wall slip would be more important. So, then accordingly you have to make corrections. That is what we see by solving this problem. So, let us say for the first data point, when D is equals to 0.191 mm, delta P is given as 45.65 kilopascal, that is 45.65 multiplied by 10 power 3 divided by L is 374 mm. So, 374 multiplied by 10 power minus 3, and then D for the first capillary of D 0.191 mm. So, 0.191 into 10 power minus 3 divided by 4. When you do it, you will get tau W is equals to 5.83 pascals. Now, similarly, gamma dot Wn apparent shear rate or nominal shear rate 8 V by D we have to get 8 V by D in terms of Q if you write, because V is equals to 4 Q by pi D square. So, then that if you make use here in place of this V, then you get gamma dot Wn is nothing but 32 Q by pi D cube. So, 32 constant. First data point when D is equals to 0.191 and then when delta P is equals to when minus delta P is 45.65 kilopascal, volumetric flow rate is 3.66 into 10 power minus 11 meter cube per second. So, that is what we have written. Pi is 3.14 and D is first capillary 0.191 multiplied by 10 power minus 3 and then whole cube. When you simplify it, you get roughly 53.5 second inverse as apparent shear rate for the first data point when D is equals to 0.191. So, you got tau W, you got shear rate also, gamma dot Wn also as well. So, then what you can do? So, now you when you get this tau W and gamma dot Wn for all the capillaries, for each capillary of a different diameter for each data set, and then you converted data whatever is there, that you write, you make a tabular column like this. So, now tau W versus 8 V by D. See, first case when D is equals to 0.191 mm, tau W we got 5.83 and then 8 V by D we got 53.5 second inverse. Similarly remaining points we got here for the same D is equals to 0.191 mm. Similarly, for other diameter capillaries also we got this tau W versus 8 V by D information. Now, for these 4 capillaries of different diameters, tau W versus 8 V by D you already got, or whatever the Q versus delta P information was there, you converted in terms of tau W versus 8 V by D, and then now you plot them. So, what you see when you are plotting this tau W versus 8 V by D, for different diameters you are getting different curves. So, this is for a smaller diameter, this is for the next diameter, and then this is for the other diameter, and this is for the larger diameter 1.1 mm. So, they are not superimposing onto each other, they are not superimposing onto each other. That means, even after incorporating the end effects, the rheological measurements of that particular fluid by obtained by capillaries of different diameter is not reliable. That means, diameter is really playing a role. You have already incorporated the end effects. So, then obviously, if no other errors are existing, so then all these even if you change the diameter, so then all they should be superimposing, tau W versus 8 V by D curve should be superimposing. If they are not superimposing, that means something is happening because of changing the diameter, and that something is nothing but the fluid slippage or slip velocity at the wall of the capillary. That is what we have to find out, as we discussed few slides before. Okay. So, now what we do, how to get that information? What we have done in the couple of slides before, we have to plot 8 V by D versus 1 by D for different tau W values. So, now what you do here, you select different values of tau W, maybe 10, 15, 20 like this, right. So, let us say when you take a tau W of something around 12 value here and then draw a straight line, and then for each curve you draw a vertical line like this wherever they are intercepting with the curves of this tau W versus 8 V by D curves, wherever they are intersecting. So, corresponding 8 V by D values you have to find out. Let us say when it is 12. So, 8 V by D for the 1.1 mm diameter is roughly, let us say 220, 1 by 1.1, and then similarly next maybe 300 when d is equals to 626 mm. When d is equals to 0.266 mm, it is roughly 380. And then when it is 0.191 mm, it is roughly 430. Right. This is what you get for 1 tau w. Now, you take another tau w maybe 17, draw a line like this, and then corresponding values you find out similar way, and then you tabulate them, and then you tabulate them as here shown here. So, I have taken tau w 5, 10, 15, 20, 25. So, for each diameter of a capillary, corresponding 8 V by d values are tabulated here for different tau w values. Right. Now, we are going to plot this 8 V by d versus 1 by d here for different tau w values. So, then you can see when tau w is very small, so then slip it is almost like horizontal line, that is slope is almost like 0. It is not 0 exactly, but almost like. Okay. So, then as you increase the tau w value, the slope of the line is increasing. The slope of the line is increasing. What does it mean? When tau w is increasing, the wall slip is increasing. So, Vs, magnitude of Vs is going to be increasing, that we can see. Now, for each of these curve you find out what is the slope. So, that is nothing but 8 Vs, right. So, that slope value for each of this tau w I plotted here, shown here, tabulated here. So, corresponding Vs you can see. See now, in mm per second, the velocity, slip velocity can be as much as 14, 15 mm per second. It is not 0, you cannot say 14 mm per second velocity is 0 velocity. Even you cannot say 0.325 mm per second velocity is a 0 velocity. Okay. So, that means that because of this slip velocity, the tau w versus 8 V by d curves were not superimposing by changing the diameter of the capillary. Okay. So, now this information Vs versus tau w, if you plot, you can get a line like this. It is not necessary that you should get always like this, you may get straight line and different nonlinear behavior also you may get. So, why do we need is, and because our true values of tau w are not exactly like 5, 10, 15, 20, 25 like that. So, because we cannot say now 4 capillary diameters, each case there are 10 to 12 data points are there, so many data points you are there. So, for each and every point you cannot do the finding out the tau w value by especially when you are doing graphically. So, then what you do, you find out the relation Vs versus tau w. Now, once you know this relation Vs versus tau w, then you can substitute required value of tau w here in this equation and then find out the corresponding Vs. Okay. So, that we do, let us say for the first data point when d is equals to 0.191 mm, we found tau w is equals to 5.83 pascals. So, when you substitute this 5.83 pascals here in this equation, then you will get Vs is equals to 0.59 mm per second. So, then you get 8 V minus Vs by d, because V already you got it. So, then that 8 V minus Vs by d, you will be getting 28.9 second inverse, this one. Like that, for all the values of tau w, corresponding Vs you have to find out, and then corresponding 8 V minus Vs by d you have to find out for all capillary of different diameters. So, that is what we get now here. So, then we have this relation Vs versus tau w relation is there. So, when tau w is 5.83, we got 8 V by d is 53.5. Before incorporating the wall slip effects, nominal shear rate was 53.5. After incorporating the wall slip effect, it decreases to the almost to half, 28.5. And then likewise you can see for all data points, you can see substantial difference between the uncorrected 8V by D and then corrected 8V by D. After incorporating the wall slip, the shear rate has decreased substantially. That is what in theory also we discussed, gamma dot S is less than gamma dot, right. And then that how much less cannot be neglected, you can see it is very large for each case here also, second case here also you can see, third case here also you can see, fourth case here also you can see. Some cases may be the difference may be less. As we discussed, this wall slip is more important in narrow passages. That means, if you are increasing the diameter of capillary, then wall slip effect may be decreasing. That means, whatever the 8V by D and then 8V minus Vs by D in details are there, values are there, they will not be very different from each other. That we can see here. When for the larger diameter capillary, still there is effect, but the difference is less. For larger capillary diameter, the difference between 8V by D and 8V minus Vs by D is very less compared to the smaller capillary diameter. Here in the case of 0.191 mm, almost 50% is reduced, but here in the case of 1.1 mm capillary diameter, 1.1 mm diameter capillaries, it decreased very less from 92 to 80, from roughly 800 to 720. Okay. So, when you increase the diameter, the wall slip effect may be reduced, but if you go larger values of capillaries, then shear stress may not be constant from wall to the center of the capillary, or the difference of in shear stress or shear rate from wall to the center may be larger if you take the larger capillary diameter. So, because of that one we have to go for the narrow capillary, and then accordingly we have to make a correction for the wall slip effect. So, now this if you plot shear stress tau W versus 8V minus Vs by D, not 8V by D, 8V minus Vs by D, which is nothing but corrected nominal shear rate. Still it is not true shear rate, it is a corrected one, but after making the wall slip correction, you can see for the change in diameter of capillary is not showing any significant effect. The change in capillary diameter is not showing any significant effect. Slightly is there, that's those things may be coming out because of the interpolations, etc. Right. So, now this one what you can do? You can find out n prime by plotting d log of tau W versus d log of 8 V minus Vs by D. We cannot take 8 log of d log of 8 V by D, we have to take the corrected nominal shear rate, that is 8 V minus Vs by D, and then find out the n prime, and then you can find out the corrected or the true shear rate, not the corrected, true shear rate, you can find it out as 3n prime plus 1 by 4n prime. This is how you can get it, true shear rate. Right. That way you can do, as we have done one example problem in the previous class. But what we do, since we already from this graph we can realize this is a concave upward curve, and then it is a shear thinning fluid, and then for shear thinning fluids, if you apply the so called power law curve fitting and then plot log of log of tau W versus log of 8V by D, then you get a straight line. So, shear stress versus shear rate, corrected nominal shear rate 8V minus Vs by D on a log law curve, if you do, you may get curve like this, and then you can find out the n prime value also. N prime you can find it from here, right. This way also you can find out. This way if you find out, you have to do n prime finding out for each value of tau W. So, but now from the curve, nature of the curve you already realized it. So, then you can apply the power law behavior whatever the so called power law fitting you can do and then find out this n prime. Okay. So, now wall slip corrected rheological data collapse onto the one curve as shown above here, and then corresponding values of the true shear rate at the wall still need to be calculated as this one, because 8 V minus Vs by d is nothing but corrected nominal shear rate, but the true shear rate you will get only when you multiply this one by this factor 3 n prime plus 1 by 4 n prime. So, wall slip corrected rheological data on log scale results a straight line of slope n prime 0.44. That means 3 n prime plus 1 by 4 n prime is coming to be 1.318. So, that means your true shear rate would be 1.318 times the values of 8 V minus Vs by d, whatever we have tabulated in the previous slide. So, 3 n prime plus 1 by 4 n prime is nothing but 1.318. So, then all these values, whatever the 3rd, 6th, 9th and 12th column, whatever the 8 V minus Vs by d values are there, that you have to multiply by 1.318 to get the true shear rate information. Okay. To get the true shear rate information, whatever the 8 V minus Vs by d values are there in the previously tabulated results. So, that 8 V minus Vs by d columns should be multiplied by 1.318 to get the true shear rate. So, the last error due to deviation from laminar flow, how to find it out. Okay. So, how do you find? So, whatever the shear stress tau w versus nominal shear rate 8 V by d, when you plot it on a log graph, in general for a laminar flow you get a straight line like this, right. When you deviate, when the flow is deviating from the laminar curve, what happens? There is a sudden change in slope, whatever the diameter of capillary you take. For different capillary diameters, the information is shown here. So, there is a sudden change in slope that you can see if the flow is crossing the laminar limit. If the flow is crossing the laminar limit, then wall shear stress versus nominal shear rate curve on a log scale would be experiencing sudden change in the slope, right. So, what you have to do? You have to, from your data, you have to strike off, you have to remove this data, because all this analysis whatever we have done for the capillary viscometer, that is true for the fully developed laminar steady flow only. So, these data you should not take into the consideration, simple. So, this is true experimental data for 15% aqueous Kavalen suspension in several tubes of different diameters. So, log tau w versus log 8 V by d plot is seen, and then data crossing laminar flow limit should be excluded for the final rheology of the fluid. You have to take consideration of these data points only. And then you can see by changing the diameter, all the points are superimposing onto each other. That means there is no wall slip effect up to this point. After this point only wall slip effect is there, and then wall slip effect in general is higher for the higher shear rates. References for this lecture: the entire lecture is prepared from this reference by Chabra and Richardson, including the example problem. Including the example problem has been discussed from this reference book by Chabra and Richardson. Similarly, other references books may also be useful. Thank you.